Can you see the screen?
Yes, sir.
Okay. So yesterday I have started the discussion on sufficiency. So this is another concept, and the basic idea behind this concept is that in the statistics, the statistical inference is based on the sample. However, if the information which is contained in the full sample can be summarized into certain number of statistics, then we need not record the whole data all the time, and we can use only the sufficient statistics. So I explained it through two examples that for example, if I am having the record of say Bernoulli random variables in the form of success and failure data, then the entire data is not required, the total number of success is enough. Similarly, in the Poisson distribution, if I want to draw inference on the rate parameter lambda, then if I consider the total number of incidents, that is sigma xi, that is sufficient. Okay. So let us consider some more comments on the sufficiency. So if T is a sufficient statistic, yes, is there any question? And T is a function of, hello, is there any question somebody is asking? Then U is also sufficient. Okay. Some other sufficient statistics. I can write, say, T1x is equal to, suppose I write x1 plus x2 plus xr plus 1 plus xn. Okay, I can split it into two parts because sigma xi is a function of this T1, because I can add these two components and then I will get T. I can write the whole data also, then that is also sufficient. Okay. X bar, if I am considering, is also sufficient. Okay, because it is one-to-one function of sigma xi. In general, the complete sample is always sufficient. Since if I write down the conditional distribution of x1 is equal to x1 given xn, x1 is equal to say y1 and so on, xn is equal to yn, then this is equal to 1 if y1, y2, yn is equal to, I can put it in different way, if x is equal to y and it is equal to 0 if x is not equal to y, where y means y1, y2, yn and x means x1, x2, xn. So this x1, x2, xn is called trivial sufficient statistic. Okay, so is this comment clear to you? That if I have t as a function of some other statistic u, then u is also sufficient. And in general, the full sample is always sufficient, which is called trivial sufficient statistics. So is this clear to you?
Yes, sir.
The statement which I wrote yesterday, that we can generate the distribution of x1, x2, xn from the conditional distribution of x. And
Sir, you are not on.
Hello.
Yes, sir. Previously, you were not audible.
And now you can hear?
Yes, sir.
Okay. And let Tx be sufficient for this family. Then given T, we can generate random variable y, which has the same distribution p theta. The first important application of this concept of sufficiency was that if I have any unbiased estimator for a particular parameter and I have a sufficient statistics, then I can consider improvement over that unbiased estimator by taking conditional expectation with respect to the sufficient statistics. This important result was actually, again, it is named after Indian statistician C.R. Rao and David Blackwell. They obtained, of course, independently. Rao obtained in 1945 and Blackwell obtained in 1947. So it is known as Rao-Blackwell theorem. So let x1, x2, xn be a random sample from a population with distribution let delta x be an unbiased estimator of g theta and let Tx be sufficient. Then there exists an unbiased estimator based on T which has variance not more than that of delta x. So basically, as I mentioned to you earlier, that when we consider unbiased estimation, an important problem is to find out minimum variance unbiased estimator. That means the one which has smallest variance. So here I am giving a general procedure that if I have any unbiased estimator, then I can consider another unbiased estimator which is dependent upon sufficient statistics and it has variance which is less than or equal to the variance of delta x. So this is a result in the direction of obtaining minimum variance unbiased estimator. So this construction was first given by Rao and in 1945 and Blackwell in 1947. So that is why this famous result is known by Rao-Blackwell theorem. So what we do, we define HT as expectation of delta x given T is equal to T. See, note that conditional distribution of x given T is independent of theta because T is sufficient statistic. Therefore, this conditional expectation will be free from theta. So I have written it as simply a function of T alone. Okay. So HT is a function of T alone. Okay. So now I consider, so HT is a function of x1, x2, xn. So it is a function of x1, x2, xn based on T alone. So we can use it as an estimator of g theta. So if we want to use it as an estimator of g theta, let us look at the properties of unbiasedness, etc. So what is expectation of HT? So that is expectation delta x given T is equal to T. You remember a property, if I have two random variables, say x and y, having some joint distribution, then expectation of gxy, it can be considered as expectation of expectation gxy given y. So do you remember this property? It was done in your probability course. That means the joint expectation I can consider in a recursive fashion. That means firstly I will consider conditional expectation and then with respect to marginal distribution of y. Do you remember this kind of result?
Yes, sir.
Okay. So this becomes simply expectation of delta x, which is nothing but g theta. So HT is an unbiased estimator. So first thing is that it is an unbiased estimator. Now let us look at the variance of this. Okay. So again, I will use another property here of the conditional expectation. See, if this
Sir.
has the joint distribution, yes.
So in the above expression. Yes, sir. How did the expectation of delta x given t equal to t became expectation theta delta x?
Yeah, that is what I
Here we
wrote
are.
here. Here I am writing that if I have joint
Sir,
distribution, then the joint expectation can be calculated in a recursive fashion or iterative
Sir.
fashion. How? Let us do this here. Let me just write it here. So expectation of gxy. So this is, we can write it as gxy fxy dx dy. Okay. So what we do, we can write it as gxy fxy divided by fy into fy. That means the marginal distribution of y dx dy. This is nothing but the conditional distribution of x given y, and this is, so I will put dx here and fyy dy. So this is nothing but this inner quantity. This inner quantity is nothing but expectation of gxy given y. Okay. And then you are multiplying by the density of y and integrating. I have written for continuous case. In the discrete case, similar argument will hold. So this is nothing but again expectation of expectation gxy given y. Okay. So
Sir, I was asking the
yes.
first line to other line. Like first we
Yeah, this is what
find expectation with respect to x, right? Expectation theta, expectation of delta x bar
yeah.
given t equal to t, we do with respect to x bar, right? Then we should get a function of t. Expectation
This
theta.
is a function of t, and then the outer one is with respect to the conditional distribution of t. This is with respect to t. So I don't have to actually put t is equal to t here. I can, because this is inside the expectation, so I can just put it like this. Okay.
So delta x bar is a function of the sample, right?
Delta x is a function of x. Yeah. HT, I have written the definition of HT. HT is expectation of delta x given t. That is what I have written the definition here. That is the way it is defined, no? HT. How HT is defined? HT is defined here. It is conditional expectation of delta given t. Is that okay?
After that statement, you wrote that it is a function of x, but it should be some function of t. That's what I'm saying.
Oh. This is expectation. Yeah, HT is a function of t. Yeah, I wrote it as a function of t only. Yes. Yeah, this is a function of t. Yes. Then this is expectation. So I'm right. Yeah, this is expectation of expectation delta x given t. So that is expectation of delta x itself, because this is, I mean, this is what I'm just trying to explain here in the below step here. You see here that this joint expectation is nothing but this. So iterative step. So this is becoming nothing but expectation of delta x given t. Is it okay or not?
Yes, sir.
So that is equal to g theta. Now the second step is again regarding the variance. So first of all, ht I am showing to be unbiased, and second step is to show that the variance of ht is less than or equal to variance of delta x. Okay, so again I will use another result here for this conditional thing, that is variance of x is expectation of variance x given y plus variance of expectation x given y. See, these results you must have studied in the probability course when you were doing the joint distribution. So these are some of the two basic results, like we write expectation of x is equal to expectation of expectation x given y, and these two results are taught. I have written in a little bit more general form here, but this is the basic type of expression here that is there. So now I will use this part here for the variance. So if we use this one, then variance of delta x, if I write, that is equal to expectation of variance delta x given t plus variance of expectation delta x given t. Now expectation of delta x given t, that is ht, so that is variance of ht, okay, and this term is a non-negative quantity. So variance of ht is always less than or equal to variance of delta x. So this is actually very powerful result in the theory of estimation. Later on it is extended to other aspects of statistical inference. Here it is for estimation purpose, then it was proved for general decision problems, that given any decision rule, we can consider decision rule based on sufficient statistic, which will be always better than the original rule. So in general, in statistical inference, it allows us to reduce the data. That means we don't need to store all the data all the time. We can consider our decision making process based on only certain sufficient statistics. Okay, and of course the question is that how to determine the sufficient statistic, that is still remaining, because the examples that I gave there, I already took certain statistic to be sufficient based on our heuristic understanding that sigma xi will be sufficient or x bar will be sufficient. But in general, for any complicated problem, how to say that which one will be sufficient statistic? As I mentioned, that one can consider several sufficient statistics in a given problem. In fact, the full sample is always sufficient. In that case, there is no data reduction. So therefore, there should be some methodology of obtaining sufficient statistics. Okay, so that one was done a little later after this definition, which is named after Georgi Neyman and R.A. Fisher. So it is called Neyman-Fisher factorization theorem. So around the year 1935, this is done by Georgi Neyman and R.A. Fisher. Actually, I will give a statement and the proof for a special case, as we are doing generally for either discrete case or for continuous case. So here also I will do only for one case. For the general case, the proof can be written in a more general fashion. Okay. Tx is sufficient if and only if the fx theta can be written as product of two terms. One of the terms is dependent upon t and theta, and the second term is free from theta. So if the probability distribution, the joint probability distribution of the sample can be expressed as a factor of two terms. One of the terms contains the parameter and the sufficient statistics, and the second part is free from the parameter. Then this statistic T is actually sufficient. So this is necessary as well as sufficient condition. So this is a very strong result, and it is known as the factorization theorem. As I mentioned, I will write a proof for one case because general proof is involving certain major theoretic concepts, and since you are only in the second year, you have not done that much of mathematical arguments. So I will not get into that complex things. Let us do it in the simple case. So let us assume, say, that fx theta is factorizable. Okay. And we try to write down something like what is probability of, say, Tx is equal to T. So since x is a sample here and T is a function of that, so any probability is nothing but the sum over all the probabilities for which Tx is equal to T. So since I am saying that it is factorizable, we can express it like g of Tx theta hx for all the x's such that Tx is equal to T. Now I am substituting here Tx is equal to T, so I can put it like this: g T theta, that will come out, and I will be left with hx, that is x such that Tx is equal to T. So now if I write down some term like this, something like this: probability of x is equal to, say, x prime given Tx is equal to T. Okay, so this is of course 0 if Tx prime is not equal to T, and it is equal to probability of x is equal to x prime, Tx is equal to Tx prime divided by probability of Tx is equal to Tx prime if Tx prime is equal to T. Just I am using, I wrote discrete case only because it is easy to express this probability of A intersection B, probability of A given B as probability of A intersection B divided by probability of B. So it is easy to explain this in terms of discrete. In the case of continuous, I cannot write like this, so it will become more complicated proof. So I am avoiding that right now. So this part, the first part is 0, so I am looking at this part only. So this part, because it is the joint probability of these two events, so it is nothing but probability of x is equal to x prime divided by the denominator part. Okay, let me write it in this fashion itself, and then I will express it. So that is Tx is equal to T. So this is equal to, just now we wrote it is g T theta hx prime divided by g T theta sigma hx over all the values for which Tx is equal to T. So this term gets cancelled out, and you are left with certain term which is actually not involving any theta. So by the definition of sufficiency, Tx is a sufficient statistic here. Let us look at the converse part. Suppose I assume that T is sufficient. Then the conditional distribution of x given Tx is equal to T is independent of theta. So if it is independent of theta, I can consider it as some function of these two terms only, the T and x here. So the left hand side I can write as x is equal to x prime, Tx is equal to Tx prime divided by probability of Tx is equal to T, that is equal to Cx prime T. If Tx prime is equal to T. Otherwise it is 0, of course, so I don't have to write that thing. So this implies P theta x is equal to x prime, that is equal to Cx prime T into P Tx T. So here so this part is a function of x alone and this part is a function of T and theta. Okay, so I mean the statement and the proof, they are not very difficult, but what is important part here is that we are able to factorize. That is the important part here. So based on this, let us consider various distributions, and based on the factorization theorem, how to get the sufficient statistics there. You will see that in most of the cases, straightforwardly, you will be able to tell the answer. Okay. Okay, so is the proof clear to all of you, this factorization theorem? Is the proof clear? Both the necessary and the sufficient part?
So can you explain the sufficient part again?
Let us look at the sufficient part once again. So I am assuming that Tx is a sufficient statistic. So if it is a sufficient statistic, then the conditional distribution of x given T must be free from theta. So I am writing down probability of x equal to x prime given Tx equal to T. If it is free from theta, then it is a function of only these two values. One is this x prime and another is this T only. So I am just writing it as a function of x prime and T. Now the left hand side, it is the conditional probability. Since I am writing the discrete case, I can explain it properly. This is probability of A given B. So this is probability of A intersection B divided by probability of B. So in the numerator, I have probability of x equal to x prime, and tx is equal to t. It will be valid only for t is equal to tx prime. Otherwise, this is not valid. I mean, it will be 0 basically. And in the denominator, then I just put probability of tx equal to t. So the numerator, it is actually intersection of A intersection B, but A is a subset of B. Therefore, we just write x equal to x prime here. So this is the numerator term, and this term I take to the right hand side. That is probability of tx equal to t. Since it is probability of tx equal to t, it is a function of theta and t alone. Okay, so I am writing it as gt theta, and c x prime t, it is simply a function of x prime. Because t is, I am taking to be tx prime, so it is a function of x. I mean, it is just a function of sample. So that's all. It is factorized here. So this is the sufficiency part. Is it clear now?
So like, can we separate two terms of like x and t comma theta? After after solving
Please say it again. Say it again. Which one you are saying?
So like from the step of c x prime comma t to like from that we can separate two separate functions of x and t.
Okay, okay. So that is all right. So t is a constant here, but this expression is valid only if tx prime is equal to t. So basically t is also a function of x prime only. So I'm just putting it as a function of x prime here. Okay. Is that okay?
Okay, sir. Okay.
Because we don't have to write separately t, because t itself is a function of x prime. So basically the purpose of this is writing that this is free from theta. It involves only the sample. Okay.
Yes, sir.
Okay. So let us look at the applications of this. So let me consider, say, x1, x2, xn following normal mu 1 distribution. Okay. So even I can take sigma square, but we can consider separate cases. Okay. So let me just write like this so that you are clear about this thing. Hello. 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 Okay, so there was some disturbance actually. So I am taking a random sample from normal distribution with parameters mu and sigma square. Okay, so as we have two parameters, we can have different situations. So case 1, sigma square is known, and case 2 is mu is known, and the third case, so here mu is unknown. Here sigma square is unknown, and the third case is both mu and sigma square are unknown. So case 1, let us consider. But anyway, in all the cases, I have to write down the joint distribution of x1, x2, xn. Okay. The joint PDF of x1, x2, xn. As I mentioned to you that once you are familiar with this terminology, then a lot of things you can answer straight away. So in maximum likelihood estimation, you had the likelihood function. Then again, you had the concept of this Fisher information. There you also wrote the joint likelihood function or the joint probability density function. So same thing again we are considering. So I think if you are familiar in one type of calculation, then all other calculations you can do. So now here I am taking mu to be unknown, so I am not writing sigma square here. So the density function is a function of variable and the parameter mu here. So that is product I is equal to 1 to n 1 by sigma root 2 pi e to the power minus 1 by 2 sigma square xi minus mu square. So that is equal to 1 by root 2 pi sigma to the power n e to the power minus 1 by 2 sigma square sigma xi minus mu square. So we try to simplify it and write it in the factorizable form. If I want to use the factorization theorem, so we write it as minus sigma xi square by 2 sigma square minus n mu square by 2 sigma square plus, see this, if you want, I can actually write the full form so that you are familiar what I am doing here. Okay, so let me write it here just for convenience. So this is minus 1 by 2 sigma square. So what I did, I expanded it. So it is xi square plus mu square minus 2 mu xi. Okay. And then you write like this 1 by root 2 pi sigma to the power n e to the power minus sigma xi square by 2 sigma square minus n mu square by 2 sigma square and e to the power mu, and then this will become sigma xi, which we can write as nx bar also, nx bar by sigma square. Okay. Maybe I can put this also separately. So 3 times I will write this e to the power. This is just to explain the things properly. Okay. So here the parameter is mu. So if I separate out this part as g of x bar and mu, and this part I write as h of x, because here sigma square is appearing, but sigma square I have taken to be known here. So this is simply a function of sample. And the second part contains the parameter mu and a variable x bar. So by factorization theorem, x bar is sufficient. So generally we say sufficient for mu, but if you want to write down, then you write full family of distributions basically. For the family of distributions Okay, so x bar is sufficient. You can also say sigma xi also, because it is a one-to-one function of this. Okay, is this exercise clear?
Yes, sir.
In the second case, see, this form we have to take again. In the second case also same thing you can just do. So the joint PDF of x1, x2, xn. But here now it is a function of x and sigma square, not mu, because mu is known here, sigma square is. So it is 1 by root 2 pi to the power n, sigma to the power n, e to the power minus sigma xi minus mu square by 2 sigma square. Here mu is known, okay? So I can consider this part as g of sigma xi minus mu square and sigma square, and this part as hx. So sigma xi minus mu square is sufficient statistic for the family So this is sufficient for the family of distributions. Normal mu sigma square positive, and mu is fixed. Suppose I had taken mu to be 0, then this will be simply sigma xi square. Okay. Let us look at the third case. So in the third case, we will look at this breakup here that we had written here. Now the joint distribution is a function of mu and sigma square both. So it is fx mu sigma square, that is equal to 1 by root 2 pi to the power n, sigma to the power n, e to the power minus sigma xi square by 2 sigma square, e to the power minus n mu square by 2 sigma square, e to the power n mu x bar by sigma square. So I can consider this as a function of x bar. I can write like this also. Okay. We can write it as a function of sigma xi square mu sigma square, and of course hx. Hx you can consider simply 1 by root 2 pi to the power n, etc. We can also write it as a function of, let me put it as h1 g1 x bar sigma xi minus x bar square mu sigma square. That also I can write. So by factorization theorem, the statistic, that is x bar sigma xi minus x bar square, is sufficient for the family so here both mu and sigma square are varying. See, let us look at the implications of these statements that I gave in these three cases. So when mu is the parameter, sigma square is fixed, then our inference purpose x bar is enough. I should use x bar or sigma xi. If sigma square is unknown and mu is known, then sigma xi minus mu whole square, our inference should be based on that. If both are unknown, then our inference should be based on x bar sigma xi square, or you can also say sigma xi square, because these are of course one-to-one functions of each other. So if I have full data x1, x2, xn, I don't have to keep track of that. For inference purpose in normal distribution problems on mu and sigma square, when these two parameters are unknown, then x bar and s square, that is the 1 by n minus 1 sigma xi minus x bar whole square, that is the sample mean and the sample variance, or the sample sum and the sample sum of squares. These are sufficient. All other data is not required for efficient inference purpose. So I hope I have explained the problem very clearly. Is this exercise clear to all of you?
Yes, sir.
Now there can be some other cases also. See, like I am having normal distribution. I have written various different cases. Let me take another case. Like in the case of maximum likelihood estimation, I had given another case. So I am considering here, say x1, x2, xn following, say normal theta, theta square. That means mean and standard deviations are same. Okay. Now what happens? So if you write down the joint distribution, see here apparently there is one parameter now because theta is the unknown parameter. But let us look at the factorization theorem and how it will look like. So it is root 2 pi to the power n, theta to the power n, and all other things whatever we wrote we will write like that. So this breakup is here. That is e to the power minus n mu square by 2 sigma square. So that is theta square by theta square. So it is simply e to the power minus n by 2. So that part also let me write here. And then we have e to the power minus sigma xi square by 2 sigma square. So that is 2 theta square minus n x bar or n sigma xi So that is, let me just look at this term here. So here I am putting mu is equal to theta and sigma square is equal to theta square. So one theta will come in the denominator. Nx bar is sigma xi. So that is sigma xi by theta. So here this part I can put as g of sigma xi square and theta, and this part I can write as hx. Okay. So although the parameter has been reduced to one dimension, the sufficient statistics is still of dimension 2. So for this family also this remains sufficient. Okay, so let us look at some other cases, other distributions in place of normal. Let us look at so I am considering say exponential mu sigma case. Okay, so that means the form of the density function is so I am considering the general form of the exponential distribution. So as in the normal distribution, here you will have several cases. So for example, mu is unknown, sigma is known, in the second case mu is known, sigma is unknown. When one parameter is known, many times what happens that some standardized value is taken. Like in the normal distribution, when mu is known, we take mu to be 0, and when sigma is known, we take sigma to be 1. Similarly, in the exponential distribution also, when mu is known, then we take mu to be 0. If sigma is known, we take sigma to be 1. Okay. But I am writing down the solution in the more general form, where it can be any fixed unknown value or fixed known value. Okay. So let us look at each case. If mu is unknown and sigma is known, then how do you write down the joint density function of x1, x2, xn? So that is product I is equal to 1 to n, 1 by sigma e to the power minus xi minus mu by sigma, and this is valid for mu to infinity. So I have used the indicator function here. So this is nothing but 1 by sigma to the power n e to the power minus sigma xi by sigma e to the power n mu by sigma, and this indicator function I can express as x1 from mu to infinity, because if each xi is greater than mu, then minimum of xi is greater than mu. So x1 is nothing but minimum of xi's. Okay. This definition we have used earlier in the maximum likelihood estimation, so I have just written it here. As I mentioned to you that if you have done one thing properly, then other things will follow immediately. So this form is again similar. So here mu is the unknown parameter. So this part is a function of x1 and mu, and this part is a function of observations. So x1 is sufficient statistic here. Okay, is this example clear? Is this example clear? So let us take the case 2 here. Is the first example clear to you?
Yes, sir.
Now in the second case, I am taking sigma to be unknown and mu is known. So I have to do the factorization in a little bit different fashion. Okay. So the joint density is, so it is 1 by sigma to the power n e to the power minus sigma xi minus mu by sigma, and then indicator function of x1. So here sigma is unknown, so therefore this part I will put as a function of sigma xi minus mu. Basically this you can also write as nx bar minus mu also. So if you want, you can write like this also. That is 1 by sigma to the power n e to the power minus n x bar minus mu by sigma. So I can split it again. I can write it like n x bar by sigma e to the power n mu by sigma and I mu to infinity x1. So this I can write as g of x bar sigma and then Hx. So here x bar is sufficient. So when mu is known and sigma is unknown, x bar is sufficient. If mu is unknown and sigma is known, x1 is sufficient. Let us look at the third case. Okay, so we again write it in a, so e to the power n mu by sigma e to the power minus sigma xi by sigma, indicator function of x1. So since here both mu and sigma are unknown, then we consider this thing as a function of x1, x bar and mu sigma. So hx I am just taking to be 1. Okay, this I am just taking to be 1. So here x1 and x bar, they are sufficient. When both mu and sigma are unknown, then x1 and x bar are sufficient. Okay, is this example clear to all of you? Then I can proceed to some other examples also.
Yes, sir. Yes, sir.
Okay, so you find it out. Okay, I am just giving you 5 minutes time. You find it out, the sufficient statistics in all the 3 cases. Okay. Okay, so are you able to solve this problem? Let me ask. Hemant Rao.
Sir, like for first one, I got mod of xi minus x bar is sufficient.
If theta is unknown, then you got mod of xi minus x bar.
Oh, sorry, sir. I mean, sorry, sir. I've just miscalculated. Give me 1 second, sir. I've just taken it reversely.
Yeah, Venkateshwar.
Sir, I'm solving now. Not
Okay.
done yet.
Okay, I am giving you another 5 minutes. You please solve it. Actually, you should try to argue that which one is sufficient. Okay, so. Okay, so now anybody has got the answers?
So is
Yeah.
it x1 in the first case?
X1, no. X1 means minimum of xi.
Yes, sir.
No, no. This is modulus of x minus theta. So how you will get x1? Okay, anybody else? Hemant?
No, sir, first one I haven't got it.
Vijay Kumar?
No, sir. I mean, I didn't get.
Okay. Anushka? Anushka? She is not there. Gayatri? Okay, I think some people are just, they have switched on and they are not there. Saikat Moi? Vinod Meena? Vinod Meena? Anybody is able to get any answer or no? Nobody is able to get any answer.
So like second one, is it the mod of xi bar minus theta?
Mod of
Xi, like sigma of xi minus theta.
sigma xi minus theta.
The second one.
Sigma of xi minus theta. Where is what happened to the mod there? What happened to mod? How did you get rid of mod?
So like I mean, like anyway theta is known and xi is unknown. Well, then like
They are known, but what happens to the mod there?
mod. So like
I
depends
mean,
upon
what
the
kind of mathematical argument you people are using? I mean, something basically wrong. I mean, I don't know. So let us consider, see the joint PDF you have to write. So here theta is unknown, so I will write it as this one. I is equal to 1 to n, 1 by 2 sigma e to the power minus sigma mod of xi minus theta by sigma. Okay. So this is equal to 1 by 2 to the power n sigma to the power n e to the power minus sigma mod of xi minus theta by sigma. Okay. So if theta is unknown, then this part I can take in hx portion, and this part involves theta here. But what is the function here you have to take? Because here full thing is coming. See, all the terms will come here, x1 minus theta, x2 minus theta, and so on, xn minus theta. So basically, you have to write all of the terms, x1, x2, xn. That means the full sample. Of course, full sample is a trivial sufficient statistic here. Now, the question is whether we can have some reduction. So you can have some reduction because all of them are coming in the summation form. So I can simply write it as a function of x1, x2, xn order statistics. Okay, because that is some reduction at least. Okay, so x1, x2, xn is sufficient here. So when theta is unknown and sigma is known, then all the observations you have to take, but if we want to have some reduction, we can consider ordered ones. Okay. Is it clear or not?
Sir, how is
Yes.
x1, x2, xn a function of summation xi minus theta?
So here, what are the terms here? You write it. So this is x1 minus theta, x2 minus theta. So basically, this is the term. Okay.
Yes, sir.
So that means all of them have appeared here. So it is a function of x1, x2, xn. But only thing is, since all of them are appearing, it is a symmetric function. So I can actually replace it by this ordered ones. So at least some reduction I can enforce here. So it is a function of x1, x2, xn ordered statistic. Okay. Actually, I mean, you can just say x1, x2, xn itself, but we want some reduction, no? So therefore, it is better if we write like this. So this is the reduction. Okay.
Okay.
Theta is unknown parameter here. So this you have to consider here, that it is a function of x1, x2, xn theta. Okay.
Yes, sir.
See, Tx cannot, see, somebody was telling sigma xi minus theta. Then this is not a statistic here because theta is unknown here. So you can't write like this. So I have to split Tx and theta separately. Okay, let us take the second case. In the second case, see here theta is known, sigma is unknown. So we will consider here fx sigma. So that is 1 by 2 to the power n sigma to the power n e to the power sigma xi minus theta by sigma. So now this you can consider as, so this part you write as some hx kind of thing, and this you write as sigma xi minus theta and sigma. Here theta is known, so this whole thing becomes one statistic. So in this case, sigma mod of xi minus theta is sufficient. And when both are unknown, then you have to take the full thing only. So in that case, we just say x1, x2, xn is sufficient because there is no further reduction possible. Is that okay?
Yes, sir.
So let me take another exercise. Suppose x1, x2, xn follow uniform distribution 0 to theta. Okay. So find out the sufficient statistics here. So the joint PDF of x1, x2, xn is, so it is 1 by theta to the power n. Since we have already written likelihood function, etc., so I don't have to explain again and again that part. So this is nothing but a function of xn and theta, and hx you can take simply to be 1. So xn is sufficient. Now, in all the problems that you are solving here, you look at that maximum likelihood estimation also gave similar terms, and here in the sufficiency also we are getting similar terms. So is there some connection? What is the connection? Can anybody guess this? Is there some connection between maximum likelihood estimator and sufficient statistic? Can you establish some connection? Anybody can answer this? Is there any connection between sufficiency and the maximum likelihood estimation? If maximum likelihood estimator exists, then they are functions of sufficient statistics. Okay, so the proof, of course, not very difficult. What is the likelihood function? So let us consider, say, let x1, x2, xn be a random sample from a population with probability density function or probability mass function, say fx theta. Okay. So the likelihood function L theta x, that is nothing but the joint distribution of x1, x2, xn. Which we usually write like this. Now, if T1, T2, Tk is sufficient statistic, then L theta x can be factorized as G T1, T2, Tk theta into Hx. In maximum likelihood estimation, we need to maximize this L with respect to theta. If you look at the right hand side, theta is appearing here. Okay, there is no theta here. That means basically I have to maximize this function. Now this is a function of theta based on T1, T2, Tk. So the solution will come dependent upon T1, T2, Tk. That is a sufficient statistic. So that is why the maximum likelihood estimators, they are functions of the sufficient statistics. Hence, the maximizing solutions will be functions of T1, T2, Tk. That is the sufficient statistics. Is the proof clear to all of you?
Yes, sir.
Let us also look at this exponential family of distributions that I had written. What happens there? So if we consider exponential family of distributions, so let us consider, say, fx theta that is equal to c theta hx e to the power sigma. I will write in the canonical form. Generally, we write qi theta, but I am writing theta I. This is just canonical form, okay? I is equal to 1 to k. So if I am taking a random sample, suppose I take x1, x2, xn as a random sample. The joint PDF or PMF so that is c to the power n theta product of hxi I is equal to 1 to n e to the power sigma theta I ti xi. So this one I will put as j here, and I is equal to 1 to k, j is equal to 1 to n. So this is c to the power n theta product of hxi. This product I can write at the end. Firstly, let me write this exponent term. So this is sigma theta I sigma ti xj, j is equal to 1 to n, I is equal to 1 to k, and this is product of hxi. So this also let me put j here, j is equal to 1 to n. So this term you can see, this is nothing but a function of T1, that is sigma T1 xj sigma T k xj, j is equal to 1 to n, and theta, and this is a function of hx. Okay, I have used vector notations here, so let me put vector here. So in the exponential family, sigma T1 xj sigma tk xj, this is sufficient. That is why, for example, I had done this normal distribution. So we got either sigma xi or sigma xi square, or both sigma I, sigma xi square, because the form is like that. If you remember the form of the exponential family for normal distribution, when we had parameter mu and sigma square, then one term was x and another was xi square. I hope these things are clear. This exponential family. whenever you have 2 parameter, 3 parameter situations, then there can be several inference problems depending upon the real life situation. All the parameters may be unknown, some parameters may be known and some may be unknown, etc. So I am just considering some of the standard distributions where generally 2 parameters are there. So at least this much you should be able to analyze. So I am giving these as exercises for you to work it out, okay? And let me take one more case. Suppose I take, say, Pareto distribution with parameters, say, alpha and beta. So alpha known, beta unknown. I have stated these problems because if you look at the research papers on these topics like estimation of the parameters of Pareto distribution, estimation and testing for the parameters of gamma distribution, etc. If you look at the papers and search in, say, Google Scholar by these topics, you will find lot of research papers on each different case. So for example, alpha known, beta unknown in Pareto, it leads to different inference problems. Alpha known, unknown and beta known, it leads to different inference results. And similarly, if both of them are unknown. So there are a lot of research papers. If you just make a simple search in Google Scholar by putting topics of this Pareto, exponential, double exponential, and so on, you will find large number of research papers. So these are all active research areas. In the classroom, I am teaching only the basic part, how to find out sufficient statistics, how to find the maximum likelihood estimators. But advanced inference or advanced procedures of the inference for various complex models which involve these distributions have been developed by statisticians because they arise usually in different situations. So like you may have a case where there are several Pareto distributions in place of one Pareto population. Now, when you have several, then there can be so many cases because each of them has parameters alpha and beta. So some part of the experiment may yield known things and some part of the experiment may have unknown things, and one needs to do certain kind of inference. So there are so many kind of problems that are there in statistical research. So I'm just giving it here and you can try these exercises. So maybe I will stop today's class at this moment. I will also like to connect this concept of sufficiency to the concept of information which I told earlier. So we considered this Fisher information measure, but what is the use of that information measure? How it is related to the information, actual information contained in the sample. So this correspondence I will give in the next class. Okay. In the meantime, you please solve many of these problems that I have given here. Okay. Is there any question? Is there any question? Okay, then I will stop today's class.